By definition, a magnet is a material or an object that produces an invisible magnetic field, allowing it to attract ferromagnetic materials like iron, nickel, cobalt, and to attract and repel other magnets. So, I mean, I'm sure a lot of people have seen a picture of a magnet. And then, fun fact, if you cut a magnet in half, you don't split the magnet, you just create two magnets. So, if you were to cut this in half, you don't have a north and a south, you just have a north, south, and then a north and south. So you just create two magnets. And then electromagnet. So again, by definition, an electromagnet is a type of magnet consisting of a coil of insulated wire or a solenoid that acts as a magnet when an electric current passes through it, but loses its magnetism when the current stops. So this is a little picture of an electromagnet. We do have a demonstration for you guys to do after we're done. But you wrap the wire around like an iron nail, and that's actually called the solenoid. So you just wrap the wire around a nail, and when the current passes through, when you hook it to the other side of the battery, it creates a magnetic field. So.
And this is the right-hand rule. So this is the first thing, one of the most important rules that you learn in physics to be able to help you identify the direction of the magnetic field. So you take your hand like this, and you're gonna point it in the direction of the current, and you're gonna curl your fingers like you're curling, like the wire curls. So like as the wire curls around, you curl it in that same direction, and the way your thumb points is the direction that the current, that the magnetic field will point to produce from your current.
You can see it right here. If you curl your fingers with the current, if it's going
So the current's
counterclockwise,
this way up, and curl the fingers up, and that points in the direction of the magnetic field, the direction of north in your magnetic field.
Yeah.
So our electromagnetic field, how does it work? Moving currents in a wire or conducting material create a magnetic field. We call this magnetic field an electromagnetic field. This is what allows us to create magnets out of coils of wire and a flowing current. So this is another example of our right-hand rule, where in this case, you circle your current and it points in the direction of the magnetic field. We got inductors and inductance. So inductance is when a current is created by changes in the magnetic field. This current will flow in a direction that tries to stop the change in the magnetic field. So when you put a charge in there and you keep moving it up and down, it produces its own charge, but the magnetic field is resisting that charge by producing its own magnetic charge, which is what is called inductance. It tries to oppose the change. And this can best be demonstrated using a conductive pipe and some strong magnets, which we do have for our demonstration in a minute.
All right, so a couple of common uses for electromagnets are any electric motors, turbines, and actuators all use electromagnets. There's countless numbers of actual products that use electromagnets, such as hair dryers, washing machines, electric fans, speakers, headphones, and MRI machines. Without the discovery of the relation of electricity and magnetism, we would be without many of our daily products that we use today. In conclusion, electricity and magnetic fields have some things in common that allow us to build very useful tools. The flowing current in a conducting material creates a magnetic field. Changing magnetic fields near a conducting material creates a current that will try to create a magnetic field to oppose the change that is occurring. So like with copper tube and the magnets. And this discovery was crucial for the innovation of many other products that we use daily today.
Yeah.
Now, with our demonstration.
Yeah. So this is our
This one first.
Yeah. I mean, we're not going to use that.
We can hold it.
We can hold it and do it, but
So you've got the copper pipe, and then normally if you were to drop it like right here, it's gonna go, you're gonna catch it. It'll drop very fast, like that. Like it just takes like half a second to fall down. But if you were to drop it inside the tube, it takes much longer to fall. So then if we want to do it again, just for demonstration, it goes much slower the second time when it comes out.
So the reason that this happens is the magnetic field is changing down. Obviously the magnet is going down. And as this magnet moves across this copper pipe that can conduct electricity, it's going to create a current. It's an induced current, which is going to create a magnetic field that's going to try and resist the magnetic field from falling. So since this magnet's falling, the magnetic field is going down. So the current that's going to be induced is going to create a magnet field that pushes up. So it's just going to slow the magnet down from falling. It won't be able to stop it, but it'll try its best to resist the change that the magnetic field is having. I mean, that's pretty much it.
Yeah, that's about it.
I've got the wire connected to the battery. You try with the head of the nail, and it lightly magnetizes it. It's not strong enough. Oh! It's not quite strong enough to pick it up with ease, but
And then if you disconnect it,
yeah, you disconnected it.
it's not gonna pick it up
It's not
at
gonna
all.
work anything.
right? So that's by definition an electromagnet. Without the current, it's not gonna be have a magnetic field. But as soon as we connect the other end to the battery, it's gonna be able to pick it up.
Not going anywhere. And then we can see if you want to record when it falls. I come record the top.
Yeah.
Like you can see it fall in here. Falling really slow like that.
Make it look like slow motion.
Mm-hmm.
And see, so we get one. Yeah, that was good.
Mm-hmm.